is basically to move ahead from the standard model to an unexplored territory that is accessible by the high energy collisions of LHC. I will describe again briefly a selection of the searches for new physics beyond the standard model. A selection of results from Exotica and SUSY. Is a selection because if we cover all the results, I would spend too much time. But I hope to give you some basic features of the major, let's say, tools that we use. I would concentrate on the tools and methods because those tools and methods could be used also for other searches or for other studies. So there is an entire zoology of new physics at LHC. LHC is a machine that is coming after maybe 20 years after the last previous machine. So the theorists had at the time, I call it a playground. They had a lot of time to produce models because there were no experimental data. So the constraints were very, very weak. And actually, at the beginning of the exploratory work at LHC, what we did, basically, we took very seriously all the models that predicted certain features, certain particles, certain state of matter appearing at LHC. And we organized a work to understand if those models are correct or not. That means that from the experimentalist point of view, this is an incredibly wide area, and the challenge is really high because it covers let's say, you will see at the beginning simple and traditional way of looking for new resonances, for example, using dijets, for example, looking for contact interaction, or looking for new gauge boson. Again, is an extrapolation of what we can do. We identify the Z and we look for the Z prime or something which has similar properties of the Z, simply a tire mass. But then once you start really going through really exotica stuff, you discover, and we did discover, that we had also to change a lot of things. For example, trigger rules. At a certain moment, we had to identify particles that could stop in CMS, could stop and stay there for a few weeks, for example. There are models predicting particles that are produced in the collisions and decay after a few days or a few weeks or a few months, for example. And this creates a challenge for the trigger. We have to understand and to prepare something that was completely unexpected. Just to give you an example of the variety of signals and topologies we have to cover. If you want to really prove or disprove a large fraction of the models that were proposed in the last 20 years. I start with some discussion on the signature, which is not complete, but at least on this slide I would like to attract your attention because it contains the basic tools that we use in several, same tools used in several contexts, and in several situations looking for different signatures, and also looking for in different background conditions. For example, if you look for resonances that could appear strong resonances in anomalies in the dijets distributions, or anomalies in the dileptons or diphoton distributions, for example, Z prime or W prime or excited quarks in large dimensions. For example, the typical background are the QCD spectrum, which is steeply folding, or the Drell-Young spectrum, which is typically folding. And you have problems to solve, which is the jet energy scale. Whenever you have uncertainty in the jet energy scale, you can move easily a steeply folding function quite substantially. You have problems once you use leptons. You have to align very well your detector, because if you don't align very well, you don't know the momentum scale. You cannot measure well at very high mass. And remember that we are looking for objects that might be also 1 or 2 TeV. So in this region, even identifying the charge of a lepton or a high PT lepton is not easy. And you can do it if you align the entire system, which is tens of meters, very well. And then you have to understand the response of the calorimetry, for example, because you have extremely energetic particles to be detected, and sometimes the calorimeter has been tuned for another region, a few hundred GeV, so you have to understand if there are saturation problems, saturation response in the calorimeter. If you want, you can use signatures like multi-jets and missing ET, for example, for SUSY. but also for new heavy quarks or composite models. Again, those are generic signatures. You see SUSY appears in different signatures. You can eventually, roughly speaking, identify or classify them as, okay, everywhere there is presence of missing ET. This is due to the fact that in SUSY we think, at least in the simplest model, there is an heavy object, which is the neutralino, carrying away a lot of transverse energy. It's not detectable directly in the detectors. And then you can associate to this large missing ET the presence of several jets, the presence of leptons plus jet, the presence of photons plus this missing ET. And again, there are different SUSY signatures that can be used, but you can use the same signatures also to try to look for new heavy quarks or a new, let's say, fourth generation of T or B quarks, T prime or B prime. You can look, for example, for photons and missing ET to look for extra dimension particles supposed to arrive from extra dimension models. So, in most of the cases, you have the QCD. Whenever you have jets, basically a missing ET, QCD is a key component. But I want to highlight the fact that you have in several cases TT bar and vector boson plus jet. This is why I spent quite some time this morning to explain you how important it is to measure W plus jet or Z plus jet or TT bar well, because they are not only interesting in themselves, but because they appear as major background components in many searches for new physics. Issues and problems in this area mostly are basically that you cannot rely on Monte Carlo to understand the background. You have to use data-driven method to understand the background. That means that use the data enriched in background component to understand the background, simulate correctly, maybe tune the Monte Carlo, and then use it to extrapolate in the similar region. It is very important to model the missing ET because you use it as a key component. So whenever there is a detector, if missing ET is a very simple object, but whenever there is a defect in the detector, you discover immediately SUSY. Whenever there is a part of the detector which is blind, you don't know, or which is not calibrated, which is responding more than expected, you immediately find events in which there is an excess of missing ET. So it requires a careful study of the detector response in the full coverage. Remember that we are trying to cover the full 4-pi region the most we can. And so on. And for rare decays, for example, in this case, for example, whenever you have leptons plus jets, in this case, for example, you look for several leptons in the events. The QCD and electric background, pure background, is physical background, goes almost to zero, but you are overwhelmed by fakes, for example. Jets faking leptons, or problems in the lepton isolation, misidentification of the charge in the lepton. So when you look for very rare decays, even the simplest effects at the detector level or at the software, the construction software level, could hit you dramatically. So again, you will see that some of these searches are quite straightforward and I would say relatively easy, but again, don't forget that behind a measurement there is always a huge amount of cross-check and controls that you should do even once you use the best understood tools, for example, the dileptons or the diphotons. I give you some example of this. For example, this happened really after a few weeks of data taking, 2010. You remember, we started at the end of March 2010. And after a few weeks, we were already ready to publish these nice distributions, in which the tool here is the digest. No? It's very simple approach. You identify digets, and you try to reproduce the cross-section, the differential cross-section versus mass. You easily arrive, even with a small amount of data, 120 inverse nanobar. Really, the first few weeks of data taking in 70 collisions, and you are able to cover masses up to 1 or 2 TeV. And then what you look for bumps, anomaly. The idea is basically, if there is a new massive object which couples to quarks and gluon, you might have a bump here and there. Then what you do, you try to fit the QCD distribution that is there, and in this case you are reasonably able to predict it through Monte Carlo. You assign an uncertainty due basically to jet energy scale. And this is an uncertainty that you want to reduce. This is why there is a continuous effort to reduce the jet energy scale to, hopefully, now we are at 3%, and the goal will be 1%, to have this band as narrow as possible, because this will increase your sensitivity. Then you subtract the background and you look for bumps. Excited quarks of a few hundred GeV or new string resonances of 1 or 2 TeV will appear as an excess of events. You don't see them, and so you can put limits. So this is really, if you wish, the simplest search one can imagine for looking for new heavy objects. And those are the plots today, because this search continues. Because in any moment, again, nobody knows, in any moment we might see something which is unexpected. And so we did, again, the search with 8 TeV data in 2012, now with full statistics. You see now that in Atlas, in CMS, we reach mass of the digest system which exceed 4 TeV, so the sensitivity is quite large. So we can explore, let's say, the possibility of having, producing LHC objects, very, very massive objects, at the limit of the kinematical acceptance. And again, you don't see nothing significant, and then you put basically limits. And today's limits are quite impressive, basically are around 3 TeV. So at the end of the day, with the increased luminosity, you don't expect to gain too much. So now this 3.5, 3 TeV limits corresponds to, roughly speaking, 5 inverse femtobarnot data. I don't expect, even if we'll be putting together the entire statistical 2012, these limits will not improve significantly. It will be a few hundred GeV more. So if you want really to have another step forward in this direction, you need to go to 13 TeV. So these studies will be done again as soon as the machine will be running at 13 or 14 TeV. Because there you can extend this reach, hopefully quickly, to something like 7 or 8 TeV, really saying something conclusive on the possibility for this model that predict these heavy, massive particles to be confirmed by the experimental observation. This is a similar study in which you study the jet differential cross-section, and you look for dijet resonance. Again, I highlight once again how important it is to check over order of magnitudes the jet production and the comparison with Monte Carlo. Because only once you have done this, take a look here, I mean, the scale is huge. These are 4, 3 TeV. Only once you have done this, you can really subtract the background, the expected rate, and look if there is any kind of anomaly. It's really impressive that we are, let's say, touching something close to 4 TeV in terms of composite. The idea is very simple. These quark are composite objects, is a la Radford. There is something happening at an angle that is large enough to claim that there is an internal structure. This is the basic approach, which is really a traditional approach in energy physics. And we repeat it with modern techniques, but at the end of the day, the idea is very, very simple. You look for something happening, hinting at a hard core within the quarks. And we are probing now something at very small scale. And whatever deviation we see, we could have a first hint that there is a substructure in the quark system, which could be another huge input in the field. So these kind of studies are relatively simple in terms of tools that you need to do, are highly rewarding if you discover an anomaly, but I would say it's also very unlikely that you will see something, unless nature will be really kind with us. So again, it's like buying a few tickets at the lottery, because you can win, but the probability is quite low. You should be really lucky to see with this simple tool something showing up immediately, and you will be in the history of physics, because this will be one of the major discoveries of the century, if we find the substructure of the quarks. This is another area in which again, the reward will be huge, because we are talking of discovering a new Z boson. new something similar to the Z bonus, it's called Z prime, decaying with the similar branching ratio to the Z, so basically coupling to quarks and leptons. There are many models that have a Z-like narrow resonance decaying to dileptons, and this was one of the search that was done again since the very beginning. Here you see why I insisted so much this morning in the Drell-Yan, because again this is the Z peak, and then the zone that you want to explore to look for something, some massive object is this one. So an accurate description of the Drell-Yan distribution at very high mass of the dileptons in this case, the muons in general, it's mandatory to perform this kind of study. Here I have a story to tell you, because I don't know, take a look to this. These are the observed limits, and the expected limits are the dotted lines. And clearly in 2012 we excluded the presence of the simplest, for example, the sequential standard model, or the simplest model hinting at the presence of a possible Z prime. But we had an anomaly here. And at the end of the year, the anomaly was still 2 sigma. You see, the green is 1 sigma, the yellow is 2 sigma. With 5 inverse femtobarn, we still had 2 sigma excess, around 950 G. The story behind this is quite nice, because for a few months, it was April, May, June 2011, we were sure that we had discovered a new boson. Within CMS, we were looking at this plot weekly, and there were every week one event coming up in this region, around 900. You see there is still, in Atlas also, there is still some hint of an excess. It's not really serious because the previous 2 bins are below. But anyway, there has been a period in which we were really close to announce the world that we have discovered a new state of matter. And that would have been clearly maybe hint of extra dimension, or maybe a new interaction, really another major breakthrough. I tell you this because on one hand, as a researcher, we should be aggressive. We should look for anomalies. We should look for discovery. If you don't look for discovery, you will never discover something. I hate people that do this kind of job assuming that they will never discover something. This is not our job. Our job is to work seriously and very let's say, with a lot of enthusiasm, with the hope that sooner or later some of us might discover something really important. On the other hand, it's also true that we should be very, very prudent, because if we do mistakes in our field, you know, mistakes are rarely forgiven. So if you lose credibility because you announce the word fake discovery, it's better that you don't show up anymore in our field. So we should find the right balance between being aggressive in looking for any sign of new physics that might show up. In your work as students, you might wake up in the morning, every morning, today I will take a look to the data and I might discover something fantastic. This should be the attitude. On the other hand, when there is something happening, then we have to switch on the criticism, really the prudence. We have to work with the same attitude, weeks or months, to kill the anomaly, to try to kill it, to try to see if it survives really all possible efforts. Luckily enough, this was done. But there was a moment in which we had a 3.5, maybe 4 sigma excess. And I was, as spokesperson, I was myself doubtful. The largest part of the collaboration was convinced, including myself, that we were witnessing a new particle. Because, you know, you take data every week, those are very clean events. Every week you get one. It looks like a signal which is growing up. And once the statistical significance is a few 3, 4 sigma, you start believing that in a couple of weeks it will become 5. For example, I informed the director of CERN. We discussed this possible signal because we could have had, we wrote a draft paper on this discovery. Because, again, we are in 2, and now I can tell openly about this. Previously it was a bit under the line of the party that we should have kept everything, let's say, confidential. But now we can can talk openly. I think it's also there is some instruction for you in this. And what we do, clearly we deployed hundreds of people to work on the signal. Hundreds of people, detector experts, software experts, statistical experts, to really try to kill it. We didn't succeed. It was a statistical fluctuation. Sometimes happened at the beginning of a certain run. So we had 10 events basically in 2 months, and then 0 events in the next 2 months. It's life. It could be. They were real. The events were real. There was nothing wrong with the events. But simply, it was a statistical fluctuation. Luckily enough, we have been imprudent to avoid any announcement or to avoid publication. But the fact that this was this with 1 inverse femtobar, and the fact that we had this anomaly, you can see that with 5 inverse femtobar, still we have 2 signals. So to kill a positive fluctuation, even once the rest of the data don't give you signals in the region, needs time. And so, since the end of 2011, we were not 100% convinced that there was nothing there. We did immediately, in 2012, at ATV, we did immediately the search. Because, again, could have been that something could have appeared at ATV. At ATV, the cross-section will become larger, so it will become even more evident. This is why we did it very quickly. In a matter of weeks, the search for Z prime in ATV, looking for, again, particularly in this region. Again, there is nothing. Now we can conclude that there is nothing there, because we don't see nothing at 950, both in the invariant mass of the diurnal system or in the invariant mass of the dilepton system. So if you put together all the information you have, this is what we do, basically putting together the 5 inverse femtobarn at 7 TeV plus 3.4, let's say, at 8 TeV, you see that also now it's becoming really 1 signal. So it's okay, now we can conclude. But again, up to a few months ago, the beginning of, say it was April, May 2012, we were still checking, because again, first of all, once you have this kind of signal, you are always thinking that your competitor, in this case, in our case Atlas, could have seen something similar, and maybe they have a stronger signal. So you are under pressure. We are not alone, so we are in a competition. And so you shouldn't risk of missing something really important simply because you are too, let's say, conservative, or you are lazy, you don't want to take a look in full detail. So the spirit of the collaboration that look for new physics should be this one. Very aggressive in looking for something that could be a signal of new physics, and very conservative once you see something to try to kill it, to be sure that what we announce to the world is really solid. This was a good example of this. Some luck also is needed, because again, for example, if you would have stopped the data taking once we had the 3.5 sigma, you would have published it. And probably we should have published with some caution, but we could have seen possible evidence of a new boson at this mass, etc., etc. So some luck also is needed. Okay, then this is also part of the, for example, one part of the work that we did to check if what we saw in dileptons, meaning dimuons and dielectrons, was real or not, was to take a look to di-tau, because there is no reason to violate lepton universality. If there is a new massive object decaying to dimuons or dielectrons, we should see something also in di-tau. And in di-tau we didn't see anything significant, so basically this was another cross-check that we did, and then you basically put limits at the end once you don't observe no excess. The search for W prime is somehow the brother search, is again, you have the W selection, you extend the W selection such that you have the Jacobian peak, which is now here, and you look into details, but it's basically very similar to looking for W at the end of the day. And you look for, since you have neutrino, you don't expect to see an error resonance, you expect to see a really broad, very broad bump, very broad excess in the muons or the electrons, depending on the resolution you have. Again, you should understand well the W, let's say, the tail of the W distributions. There are also components of Drell-Yan and dibosons coming in, particularly in high energy, in the high mass region, and you conclude that there is no heavy boson at the level of today, let's say 2.5, 3 TeV. This is another interesting search tool, and it's quite powerful and is relatively simple. Basically, you look for missing energy and a radiated jet or a photon. Basically, the idea is that if you produce in quark anti-quark annihilation, you produce a neutralino and you have an initial state radiation of blue or photon, the final state basically is very simple. There is nothing but a jet and a photon. So basically, you look for monophoton and monojet, nothing else than large vicinity, because you have a large fraction of energy there. So that the basic selection is basically to have a leading jet or a leading photon and nothing else but a huge missing ET. You see the distribution of missing ET reaches 1,200 UG. So clearly the main background, since you request a large missing ET, the main background is invisible Z or W plus jets, basically. But invisible Z is one of the major things you have to handle. You have many events in which you have large missing ET, and then once to the Z, for example, going to neutrino, you have associated a jets, you can have a photon, or you can have a jet, so you can misidentify this Z plus jets production as a single photon or a single jet plus missing. Unfortunately, there is nothing there, so you put, again, limits on large extra dimension that could produce a state of matter decay in this final state, and limits are at the level of 1.6 up to 3 TeV. This is another thing which is absolutely fantastic, because I was surprised myself, because you can use it as a complementary approach between the direct LHC and dark matter experiments. Basically, you can use the same topology, so monojets, photons, missing ETs, to put limits on dark matter. So you can look for really something very heavy, or you can look for something that could be a generic form of dark matter. In this sense, the collider experiment can cover much lower mass and also very high cross-section with respect to the direct dark matter detectors, like the underground detectors that of which there will be lectures soon. And this is the results that have been obtained in two different scenarios. Here you see in different tune the exclusion limits that in terms of cross-section of the weakly interacting particles versus the mass. And you see the huge amount of mass. The data spans between 1 and 1,000 GeV. There are two independent interpretation, if you wish, one spin dependent or spin independent. And it's nice to see, okay, that there are here, I don't know if you can read, but there are xenon, cogent, the best detectors for dark matter detection in underground facilities. And there are areas in which clearly they can do better, but there are areas, for example, in the low mass region in which the detectors at LHC can provide additional information. So it is somehow complementary. And again, this was quite a relatively easy analysis based on tools that were developed really to look for these exotic objects. And this is another case, again, you have to study diphoton, and you can have a graviton due to the excitation of large extra dimensions. So you might have something like a narrow resonances going to diphoton, appearing at a mass, let's say, between 1 or 2 TeV. It could be Kaluza-Klein states, could be narrow, could be broad, so you have to look for any kind of excess that deviates from basically the diphoton, gamma plus jet, and dijet natural background. You don't see nothing, so basically we put limits also here. And this is another example of similar searches in which you look for a massive neutral boson, looking for hunts in the spectrum of the invariant mass of the TT bar. But again, the absence of any kind of bumps in the tail of the distribution allows you to only to put limits. This is another search which is interesting because, again, in principle, we could reach dimensions in which gravity could become very strong. We could produce microscopic black holes at LHC. And macroscopic black holes can be, this could be an appearance of this kind of events. They appear quite democratic. There is a lot of energy. We call the sum of all the objects in terms of transverse energy, the energy carried by leptons, the energy carried by photons, all together, to give you an idea of the energy of the object eventually produced. So you cut on overall transverse energy produced at the level of a few TeV, and you have a certain number of objects, being these object jets or leptons or missing ET. And once you exceed 3 or 4 or 5 or 6, you enter into the search region of eventual black holes. A black hole, a micro black hole, for example, of 1 or 2 TeV, will appear in this ST distribution for objects larger than 4 as an excess in this region. Since, again, data point seems to be consistent with the background, which is basically multi-jet to CD, first approximation, although the events are very spectacular, we can put limits on the production of microscopic black holes at LHC at the level of 70. So this is just a selection of the many more, let's say, limits or studies that have been done by CMS in this case, by Atlas in this case. So you see that simply from the number of lines, you realize how complex it is, the search for exotica channels in the two experiments. It would be frankly impossible to cover them in lecture. And this is a typical, I like it because SUSY is somehow similar. This was just one conference, Morion last year, and just only CMS. So this is where maybe all the plots that were shown at this conference. But SUSY is really quite an important subject because still there are good reasons to believe that could be a real symmetry of nature. And despite the fact that, as you will see, we don't have evidence for anomalies hinting at the presence of SUSY in our data, still the fact that SUSY provides a good candidate for dark matter, and the fact that we have discovered the Higgs and that is light. So in principle, we could have new physics to stabilize its mass, and SUSY could provide a really nice way of cancelling the interference to such a way that, so it is really elegant in this respect. And still, there are good motivation to believe that nature could have chosen SUSY as a symmetry to be explored. But we have to be careful because there are so many parameters in SUSY that in this pictorial view, not to be taken too seriously, but you see that basically what we've done so far, we have somehow explored a very small amount of parameter space. This is the constraint minima supersymmetric models. And if I would like to depict really the entire phase space available in different choice of the SUSY parameter, you really realize that we are really, we cannot really say much overall. We can say what we see, that we have not, within constrained model, within simplified model, within, let's say, even the most popular models, so far we have not seen any kind of signal. But the exploration is really at the beginning. I think also that it will be very difficult, even 10 years from now probably, to say, okay, if you discover SUSY, it will be easy. But if you don't discover SUSY, to claim that SUSY is dead and there is no SUSY and you have to abandon this theory, it will be tough, even with additional experimental evidence. Because again, playing with tens, 100 parameters, you will find always a corner in which you might be able to accommodate the experimental data. So this is why we have to continue. We have to insist. We have to be patient. We have to insist, and we shouldn't work with prejudice. we have to try to understand what is happening in this area. I make a short digression because this is the only result I mentioned of LHCb because it's very nice. It's a way to probe SUSY through very rare decays, in particular the rare decays of B sub S and B sub D in dileptons. These decays are doubly suppressed in the standard model because are forbidden at 3 level. There is a recipe suppressive factor. And so basically the predictions are very, very small, are basically 3 10 to the minus 9 for the B sub S to mu mu and 1 10 to the minus 10 for the B sub D to mu mu. And so it is interesting to measure this branching ratio and to probe this decay because this is somehow very sensitive to new physics. In particular, in the minimal supersymmetric model, the branching ratio is proportional to the 6th power of the tangent beta, which is an important parameter. So and this is a very powerful tool and there were many hopes, frankly speaking, up to a year ago, to see some anomaly there. The search was done by CMS, Atlas, and LHCb, but LHCb was really the first one able to measure the branching ratio. So we produced results last year with better and better limits, but this result that was presented last summer was really the first one measuring still with the big errors the branching ratio. Basically, you take a look to this area in which you expect to be sitting the peak of the B sub S to mu mu, and very close by in this green area you should see the peak of the B sub D to mu mu. And clearly there is quite a tricky because you are on a background which is not very regular, there are combinatorial components here, and so it's really a very tough analysis. That was done extremely well by LHC. And here you see for different boost and decision tree output, which is increasing sensitivity, the fact that you do still see the peak of the B sub S to mu mu emerging from the background as soon as you go for higher sensitivity bits. And this allowed the collaboration to measure the branching threshold, which appears to be fully compatible with the standard model. Again, if you wish, this is, again, we cannot stop because again the errors are still too large. So these numbers is compatible with 6 or with 0, no? So the errors are still too large. But clearly, in this plot, there are many plots that you can use in which there are different models of SUSY in which you try to constrain the model using the current information on the branching ratio B sub D to mu mu and B sub S to mu mu. And this is where we were before the last measurements by LHCb. We were already very close to the standard model. Still, we are already still there. We are not moved too much from these limits, but clearly all this region is becoming less and less common. So again, you should see at SUSY as an area that could be constrained with direct searches, looking for neutralino, or looking for squarks, or looking for stops. Also an area in which indirect searches through precision measurement of decay modes could be very effective. This is one example. Then I go through some topologies of the SUSY. A fundamental problem of SUSY is that most of the models depend on many parameters. And so, depending on the parameter, you change the production and decay mode. And so, in principle, you have an infinite amount of topology. So you have to make a choice. And what we did, we chose some benchmark points, some benchmark models, and we decided, together with Atlas, to use them as benchmark scenarios. And those were studied in more detail. Sometimes we have a very generic features, but just to give you an idea, in a typical SUSY search, based on gluino strong production, so gluino has core production and decay. So basically production is strong interaction, meaning that you have very large cross-section. So cross-section seems to, SUSY, if it is real, is not a rare event at LHC, because the production cross-section are very large in case of strong interaction. The decay details depend on model parameter. However, once you produce an heavy state, at the end of the day, it decays to jets, lepton, photons, and missing it. You might remember at the beginning I went through this series of topologies. And this is basically a summary of what I'm saying. We produce a SUSY pair here, and this SUSY pair goes to, at the end of the day, produce jets, or here and there, produce leptons, and produce missing ET through neutralino production. So, at the end of the day, in this decaying chain, you always find basic ingredients, which are many jets, large missing ET, presence of leptons or photons if you decide to explore, let's say, smallest branching ratio in which leptons are produced, for example, due to the decay of the atoms. So this is a summary of the searches and the strategy that, for example, CMS has followed. So if you want, if you use only hadronic decay, so you look only for jets and missing ET, you ignore leptons. Then you have large backgrounds due to standard model and QCD, but you are very sensitive to strongly produced SUSY, because clearly this is a way to probe strongly produced SUSY. If you add a lepton, or you add 2 leptons, clearly you go, if you increase the number of leptons, here you see, the background, so it's very unlikely that the standard model background produce 2 or 3 leptons. So you have, for example, TT bar background, but if you increase the number of photons or leptons, basically you decrease the background, but clearly the statistics becomes very low. So here you are looking for very rare events, a handful of events. And in this case, you are less sensitive to strongly produced SUSY. The branch, let's say the cross-section time branching ratio are very small, and you are, on the other hand, more sensitive to gauge-mediated SUSY. So there is some complementarity between the two. So basically, what is done by ATLAS and CMS is concentrate on these topologies, and the name of the game, the challenge, is basically to understand the background using data-driven techniques. So if you say SUSY, you should be prepared to spend months of work not on the signal but on the background. This is a very simple statement. Being this background, a large QCD background, or being a low rate background due to fake leptons, for example, is just the same. If you want to study detail, you have to work really months to be able to convince yourself, to convince the collaboration that you have understood what you're doing. These are a few examples of this study. For example, only jets, so 0 lepton. 0 lepton means that you look for jets and missing it. And here you see the effective mass of the object. You look for a deviation in the distribution of the effective mass. Basically, there is nothing appearing up to a certain region, and this way you can put limits on the again within a certain model on the mass of squarks and gluino that eventually decay to standard model object Q plus neutralino. And you see that the dominant background, no surprise, is Z to nu, Z invisible, that produces a large component of missing ET. At the end, you have limits at the level of 1 TeV. But again, be careful, because this applies to squarks and gluino, does not apply to the third generation, to stop and spot. On this we have to do another study. So the fact that we don't see squarks and gluino at the level of 1 TeV in minimal supersymmetric constraint models does not mean that there are no stop or spot maybe at a few hundred GeV. So we have to be very careful there. This is another example of same for CMS, same sign dileptons, Q missing ET. Now you see that, I don't know if I didn't highlight, in the previous plot, you see numbers were thousands, hundreds of events. Now, once you add two leptons and missing ET, you see numbers are 20, 30, etc. So we are already talking a very small number in which any instrumental effect might play a role. For example, charge misidentification, prompt, non-prompt, so there are, let's say, mostly instrumental effects here. And here you see the sensitivity is smaller, is lower. On the other hand, it's very important to have different signatures. In particular, if we would see a signal, we would like to see a signal in excess, not only in one channel, but also in multiple channels. And so this is why we pursue this approach in which we use different tools to look for SUSY in the same region. Some of them are more sensitive in a particular region, some of them are less sensitive, but putting them together, particularly in case of discovery, we could be sure that what we see is real and not an artifact. This is basically the summary of all the analysis. You see, the name here corresponds to different tools that have been used, different variables used to study the constraint minimal supersymmetric in CMS in this particular case. You see, the lower sensitivity are multi-lepton, dilepton, one lepton. Higher sensitivity are full hadronic, basically. This is the same story. And you see also that since M1/2, you have to see here, basically. The squark limit is between 1 and 1.5, while the Guido limit is around, let's say, 1 TeV. So we are really pushing the limits toward 1.5 TeV. And this is another example, is another interpretation. Clearly, all these results are model dependent. If you change the pattern of the mass, the limits can become weaker, as in this case. The limits at 1000 GeV could become a limit at 600 GeV if you allow the difference of mass between neutralino and the mother mass to be 0 or 200 GeV. Again, it's tricky, SUSY, because whenever you have an experimental result, you can interpret in different models, and you can get different absolute value of the constraints. But this is an important slide. I want to highlight to the point that there is still room for natural SUSY. This was the, let's say, in this, this is the mass of the SUSY states, and this is the first and second generation. This was what we are currently exploring, was the prejudice on which we worked since the very beginning. That squarks and Guido are the lightest supersymmetric particle together with neutralino, and they are a few hundred GeV of mass, and they are produced, since they are light, very copiously at LHC, and we might look at them very clearly using miscibility signature. So it will be quite straightforward to discover SUSY. Actually, many people were convinced that we would have discovered SUSY much earlier than the Higgs boson. This was the prejudice that was widely distributed just a few years ago. But now, in some sense, this is probably, it's become, I don't think it's excluded, but it's less and less probable. But still, we could have the opposite. Nobody tells us that that there is a symmetry between matter and supermatter. No? In matter, the lightest family, the lightest generation is the first one, and the second, the third one is very heavy. The top is up. But we could have the opposite in supermatter. In supermatter, we could have the lightest squark being the stop or the bottom, and to have the first and second families to be very heavy. There is no reason why this shouldn't be the case. And so, if you take a look to this possibility, which again is consistent with the theory, now we have also a Higgs boson here. The spectrum could become completely different from the one that we were assuming. Now the first and second generation could sit at 7, 8, 9 TeV. So not surprised that we don't see anything with the tools that we have used, jet or missing it. Could be easily because they are too heavy to be produced. But what could be accessible could be gauginos, the W and Z of the supersymmetry, the partners, or could be the stop and bottom, the third generation, that could still be in a region between a few hundred GeV and 2 TeV. So again, but this state we have not looked properly so far. So, for example, a stop would decay in top, so there will be a play to be played by a role to be played by the bit-adding techniques. So, what is happening in CMS and Atlas in the last year, since the first round of searches for strongly interacting SUSY and first and second generation being the lightest, is becoming less and less probable. Now we are reviewing all the analysis, basically trying to see if we can identify something completely different, which is still SUSY, but with a completely different spectroscopy. And this is a new challenge, because we have to again start from scratch in some sense. So now the production is not only strong production, but there are direct gauge and stop and bottom production, which is the cross section are lower, and the decay is different. For example, we don't have large missing ET, for example. So a completely different trigger, for example. At a certain moment, we have also to review that if you are able to trigger on these kind of states, because if you trigger, you can study, but if you don't trigger, you don't have anything to study. So basically, there are two major strategies. One is cascade decays with boosted stop and bottom emissions, another direct production of stop and bottom, like a top pair-like events with marginal missing ET. So we look for something which looks like a heavy top or a heavy bottom without basically missing ET in the event. And these are, for example, the limits that we can produce on the stop production cross-section as of today. But you see that the limits are weak, are 450, 500 GB. So we are really at the beginning. And this is why, if you remember that we could have a stop up to 2 TeV, we cannot say we don't see the stop, therefore there is no stop. We have to wait. And probably we have to wait the new run of LHC, because working at 13 TeV will be extremely beneficial for this purpose. The same is true for direct stop and bottom. You see the limits are, I mean, for the Quarks and Gluino we reach 1200, for stop and bottom we are barely around 400, 500. So this is why we are really at the beginning. The same is true for Atlas. This is a summary of the Atlas searches with direct production in stop and direct production. And you see that at the best of our effort, we are studying something at the level of 500 GB. So too early to state that there is no stop, no bottom, and there is no supersymmetry. So we have to be patient. This could be even another challenge. We could even have more challenging scenario. This is a transparency by Nima Kali Ahmed, in which we could have split SUSY, basically. It could be even worse. We could have fermions at the level of 1 TeV, scalars at the level of 100 or 1000 TeV. So again, still SUSY could work in this condition, although the fine-tuning is quite impressive. But this would imply, for example, and on this we are working, for example, because again, we cannot exclude that nature have chosen models that appear to be less elegant and less natural than others. Because in this case, we could have a variety of long living objects, going from prompt to stop particles. This is why something that I alluded to you before. This is why, for example, in these searches, we look for particles that could decay in the detector from microseconds to weeks after the collisions. Again, you have to prepare a good trigger. You open the window during the collision, and then you open again at a different time, and you do the search, assuming that there is something heavy produced in the detector and decaying not promptly, but decaying after a certain delay that could be as long as a few microseconds from a day or a week. This is the status of the Atlas SUSY search. To guide the eye, take a look. This is 1 TeV. So basically, it's 1 TeV for the strong production, and basically half a TeV for bottom and stop. And this is basically a grand summary of the searches. If you ask me to summarize in simple terms, we have excluded, we think it will become really tough for constrained minimal supersymmetry to foresee particles in the range 1.2 TeV. We see nothing there. This does not mean that we don't, we still have room open for bottom and stop at a level from a few hundred GeV up to a few TeV. This will be the challenge of the next data taking period. We exclude massive gauge boson, like the one predicted by the sequential standard model at the level of 3 TeV or more, excited quarter level 3 TeV or more, and this again is somehow a picture that should be taken into account. If you want to build a new model, you have to take into account seriously this experimental constraint, and that's the end. It is a pity that we have not discovered new physics at LHC. On the other hand, tomorrow you will see what we've done in terms of understanding electroweak symmetry breaking. So I would be I mean, it will be excessive if you wish to have a couple of major discoveries in the first 3 years of running. Today, LHC is stopping, so we have the first 3 years of running. And for me, having had a major discovery is already an incredible breakthrough. I would be really extremely surprised that in the same 3 years we would have discovered this boson and SUSY or extra dimension in new physics. So we are not a generation of physics so lucky, so we should be patient. Thank you very much.
Questions, please. I have a question about searching for quarks in a structure. Maybe I missed something, but am I understand right that you don't know exactly the partonic functions, so and you didn't see interaction of two single quarks. You always interact some bunch. So how you could you see that quarks have in a structure? I'm a theorist. I don't know experimental science much. So could you explain simple terms?
Yes, it's true that a proton is a complex object made out of quarks and gluons, but it's also true that the hard scattering process, if you want to produce a mass of a few TeV, like the mass in the Dijkhead distribution I showed you at the beginning, 2, 3, 4 TeV, those events are produced by the hard scattering of two partons in the proton. So we know that this is the other, let's say, partons do participate to the interaction, but only producing soft particles, underlying event effects. So the real hard part of the interaction is due to the hard scattering of one of the.
So it's always two single quarks, or two single
gluons in quarks or gluons. What we do something very similar really to the Radford exercise. We look for what happens if there is no structure, if there is no internal structure in the gluons or in the quarks. Basically, you have a steeply falling function, uniformly falling on a logarithmic scale. If at a certain point you hit an internal structure, you have objects at an angle which is not the one predicted, or if you wish, you have object at a mass which is larger than the mass that you predict using simple exponential functions. So you look for a bump. But it's exactly the same approach that was used by Lord Radford at the beginning of last century, to look for an internal structure of the atom. So we continue to do the same. And we probe smaller and smaller dimensions, hoping that at a certain moment we could see something which deviates from the normal scattering. So.
Okay.
I think the question was about our knowledge of momentum distribution of quarks and gluons. If you change the momentum distribution, you change the slope of this curve, right? So as far as I understood, the question was, from where do we know these distributions of quarks and gluons, from which you search the deviation?
Yeah, as of today, I don't know if you remember the yellow band that covered the experimental data, for example, the Dijkhead mass distribution covers the jet energy scale, which is much larger than any effect of the PDF that are unknown. Those are not the best process to constrain the PDF. To constrain the PDF, what is advisable is to use electroweak processes, like production of W and Z, eventually plus jets, like charge asymmetry in the W production. Those constrain the PDF strongly. And if you look for processes so large, masses so large, in first approximation you might neglect let's say the error that we have due to the PDF in this curve. This is what we do.
So the uncertainty is too small, yeah?
Yeah. With respect to the effect that you look for, you see the effects are macroscopic, are, let's let's say, bumps that you would see if some of these excited quarks, for example, or inner structure of the quarks would be real, you would see it at the beginning, maybe with some small fluctuation in the data, but there would be no doubt that you would be able to collect statistics to have it done properly.
Tevatron produced several hints of new physics. Well, this could be obviously the effect of the last.
It's a known effect.
Yeah, the end of the experiment. People often make such. Okay.
So there were
attempt to see something completely new. But what is the status at LHC? There were two probably major hints. One is CP asymmetry in dileptons, and another in asymmetry in the top production. Yeah?
There was another one, is the MJJ bump. You don't remember? There was a claim that there was a bump in the MJJ invariant mass at 150 GeV.
Yeah, but this disappeared.
This was
long time ago.
An effect of the last year of running, in which it's quite usual that experiments really publish whatever they have, including anomaly on which they study for long, and then they publish it. They are sometimes, those are considered hints of new physics. But I was in CDF at the very early stage. I always remember that the first time that you collect some statistics, in the tail of the distributions, you always find something. The tail of the distribution of the invariant jet mass, for example, was a typical example of, I remember that the hot discussion on compositeness of quark at the level of 700 GeV in the very first preliminary data. So we have to fight statistical fluctuations. So far, we have looked carefully at all possible hints of something anomaly. There, I would say that Atlas and CMS are well equipped to look for something like the dijet invariant mass bump, while LHCb is better equipped to look for anomalies in the flavor violation in the flavor system. That there was already some tension with the standard model produced a couple of years ago. The only thing that, to my knowledge, survives to this crossed scrutiny is this asymmetry for the top pairs, on which, as I was telling you this morning, we don't have enough sensitivity yet to say something conclusive. So, or the Tevatron experiments will review the analysis. Sometimes they invent new tools, and they will be able or to enhance the significance of the effect, or maybe to review it, or really we have to wait a few years before LHC will be able to say something significant on this anomaly, if it is real or not, directly. Indirectly, we have already proven that if the anomaly is due to some massive state, we can directly see the massive state, and we don't see nothing. So, if you wish, a weak point of the anomaly of CDF could be that if it is due to some massive object at the level of 1 TeV or so, it will be very difficult to escape our direct detection. But this is not enough. What is needed is really a direct comparison of the measurement of the quantity that shows the anomaly to be sure that okay, we confirm or not. So on this, I think the room will be still open.
No other questions?
Sorry, but I have a question. I didn't understand very well if you expect to see small black holes or something like this.
No, we don't expect, we look for. We are physicists, so we are neutral in terms of predictions. I would be very happy to discover some of those. The problem, the message I want to tell you is the following, that in LHC we have the tool to explore this production, this exotic production mechanism, to probe these theories very seriously. With the machine running at 7 TeV, we have already exceeded the scale of the order of 4 or 5 TeV, depending on the number of extra dimensions you assume, because there is always a double assumption there. If we move to 14 TeV, this search will continue. Again, it will not be conclusive. The fact that we will not see, likely, I think, no dramatic increase of strength of gravity. It will be another major breakthrough in science. At LHC, at the scale of 10 TeV or 13 TeV, does not mean that the models are completely wrong, because they are able to move it. This kind of model are really flexible. They can move it to the scale to 20 or 30 TeV, and we are, as experimentalists, we are lost. But this search will continue. This search will continue because the experiments are very well equipped to identify any possible signatures of black holes. If a black hole will be produced, it will not escape the detection, because detectors behave very well, and the events are so dramatic that it's relatively easy to identify them. You ask for 10 jets or so, you ask for energy, transverse energy produced at the level today of 3 TeV or 4. Tomorrow will be maybe 7, 8, and so clearly you are left with very small background, and so which is well understood, because you have the points in which basically there is no many objects, so you can study SUSY very well. So it is a clean search in which any signal of microscopic black hole will be easily detectable with the LHC detectors.
Thank you.
So maybe I missed that, but what are the events which you're looking for as the candidate for the long-living particles? Long-living particles?
Yeah, it's typically events that are trapped. There are several candidates. There are events that have, let's say, a speed which is lower than the normal speed. That means that they reach, for example, the muon system after the bunch crossing. So usually at the trigger level, we open the detector during the bunch crossing, so we allow the particles fly through all the chambers, so we allow the time flight to allow everything will be collected, and then we close again and we digest information. For events that fly at different speed, for example, we have to change this rule, and actually what we do, we apply trigger rules in which we open the window as normal during the collision, we allow the time flight of particles reaching the last chambers of the detectors, and then we open again the gate after a while at intervals to see if there are something happening. Clearly there is always something happening. Most of the cases are cosmic rays. The typical background of this, when you look for something which is not in time with the collision, is a cosmic ray penetrating through the ground and penetrating through the detector. So the typical cut in this search is to look for tracks, events, pointing to the interaction vertex. 99.95% of the cases you see something, a release of energy in a calorimeter, or some muon stub, or some tracking stub, but those are away from the interaction vertex because they are cosmic ray going through the detector at different angles. And since the precision of the primary vertex is at the level of a fraction of a millimeter, so the probability that you have a cosmic ray in time with the opening of the trigger and passing through the interaction vertex is quite small. So this search is quite clean. It's quite clean. Again, if something will be produced and will spend time in CMS before decaying, or will fly through CMS spending seconds or hours, the detector will be able to see it.
Those things that you're detecting in time after the collision, they're the remnants of the decay of these long-living particles, or they are the long-living particles?
No, could be long-living particles, not like
the
heavy muons, for example. muons which is really slow and going through the muon system, or could be the decay products of the living particle that decay after, not after a fraction of infinitesimal fraction of a second, but decays after, let's say, a minute. We consider all possible options. And if you take a look more closely to the plot that I show, this plot covers between, let's say, 100 nanoseconds and weeks. So basically, we explore the possibility there is something happening in the detector later on with respect to the collision time, later on at the level of 100 nanoseconds, so 2 bunch crossing, and you open the gate even a week later. This is what is done. We publish papers, again we don't see, so we put links.
It goes far away from your detector and from LHC actually.
No, but again, there are, here you see different, there are particles which are stopped into the detector, there are particles that are slowly moving into the detector, there are particles decaying to the detector. Yeah, so we have to keep an eye open to all possible signatures. So particles that are stopped into the detector, so releasing energy after a while, particles that are slowly moving, so like a slow muon, which leaves tracks everywhere like a muon, but on a time scale of minutes or hours, or particles that decay into the detector later on with respect to the collision time. It's very tough, as you can imagine, because, but again, this was not foreseen at the beginning in CMS. It was something that was introduced once our friend theorist told us, oh, take a look because you might have this kind of phenomenon. So this gives you also an idea of the flexibility that is needed. And it was a young student that proposed the trigger, because at the beginning it was not foreseen. It was a student that was willing to do this work as a thesis work, and he convinced the collaboration that it was worth to spend time. Organizing a trigger is a big effort. You need to do a lot of work. And they spend time to optimize this trigger for these exotic particles.
And another question about micro black hole. What do you consider as a micro black hole? It's some massive object with which give you many jets, for example, 10. Please give a definition.
No, we give a definition in terms of the models that have been produced. So for us, we consider a micro black hole an object that evaporates, decays immediately, a very massive object. Limits are already at the level of, they were already at level 1 or 2 TeV. We have extended the limit up to 3 or 4 TeV. That decays democratically. So if you take a look to the decay modes of a black hole, it decays to everything. It decays to jets, to leptons, to missing T, to photons. So this is why we call objects. So we take events which are quite symmetric. You might have noted that they are quite symmetric, in which you have objects, being these objects jets or leptons, IPT leptons, or missing ET, or photons, or muons. We count the object and we see if there is an anomaly in the production rate of this object that QCD predicts on a steeply falling, let's say, distribution. If there is an anomaly there, we attribute this anomaly to the production of a massive object decaying in this mode, which is typical of a microscopic black hole. To conclude that it is exact is another story, but would be, again, just showing the signature that we have an anomaly and we have a signal something is happening, it would be major discovery. This is for you next few years.
Okay, thank you, speaker, again.